let's go to the next talk by Robin Corbet, who will be telling us about the superorbital modulations in wind systems. Robin, yes.
Okay, hi everyone. Thanks for giving me the opportunity to talk today. So, as I said, I'll be talking about superorbital modulation and primarily in wind-accretion high-mass X-ray binaries. And this is mainly based on a paper which appeared in AppJ at the beginning of the year. There's quite a lot of stuff in here, so hopefully I can manage to get through it in time. Now, superorbital periods in HMXBs had been known for a long time. Primarily in systems like Hercules X1, which we're going to be hearing about later today, SMC X1, LMC X4. In that case, the primary stars are close to filling their Roche globe, and we have a persistent accretion disk. And the most popular models of the modulation is caused by precessing accretion disk, perhaps due to radiation-induced warping. But in the systems I'm talking about here, the accretion takes place from the stellar wind. So initially 2SO114 was found by Farrell et al. And then we found 4 other systems, which we published in 2013. Now, in this case, we don't expect to have a persistent accretion disk with a lack of angular momentum, and so a precession model won't work. And so it's puzzling what could be causing the superorbital periods in these systems. In addition, there is a possible correlation between the superorbital period and the orbital period. Some models have been proposed, including 3-body systems, stellar pulsations, and structure of the wind, which I'll talk a bit more about today. But initially, it was unclear how any of these mechanisms could give such a correlation between superorbital period and orbital period. Now, I'm mainly talking about 1538 today and how this is adding on to the body of knowledge of these systems. So obviously, it's been known for a long time. From the Uhuru days, it's rather bright. And so it's been long known and well studied. It's got about 500-second pulse period. It eclipses with a 3.73-day orbital period. The eccentricity isn't well known, but it's probably not very high. And it's accreting from the wind of its B0 supergiant companion. So the primary data we did was using long-term observations from 2 satellites. In the top panel, we have the pulse frequency as measured primarily by the Fermi GBM, at the beginning some integral data points in blue there for the earlier data. So the pulse flux in the middle panel. And in the bottom, we have the flux measured by the Swift BAT. So this is all hard X-ray data. Now, if you take the power spectrum of the BAT light curve of 1538, you see very strong peaks due to the orbital modulation. So this is plotted versus a period rather than frequency. The harmonics are all off to the left-hand side there. But in addition to that, there's what looks like a tiny blip compared to the orbital modulation in the power spectrum, especially in the resolution here, it looks like almost nothing. But it's not that at all. So to get a better look at it, what we did was we got rid of the eclipses from the data. So this is the BAT light curve folded on the orbital period, very prominent eclipse there. So we removed the data between the red lines. And then we went from the power spectrum at the bottom to the one at the top. And you can clearly see that that was a superorbital modulation, extremely high statistical significance. And one weird thing is that the superorbital modulation is at 14.913, exactly within the uncertainties equal to 4 times the orbital period. This shows the BAT light curve folded on superorbital period. In the bottom, we have the eclipse data still included there, and you can see that they're, because it's in sync, they're very prominent there. The middle and the upper panels show the data folded, 2 different time resolutions with the eclipse removed. So you can see where the chunks are missing from the data there. So we also wanted to look at the long-term behavior of superorbital modulation. So on the right-hand side, you have the BAT data shown with its dynamic power spectrum, going from early times at the bottom to later times at the top. You can see that for the later times, the modulation changed from being primarily at the fundamental frequency to the second harmonic. I'm not sure my cursor shows up here, but it is becomes prominent there. The modulation goes away at the fundamental. And now the frequency changes from the bat, the top panel on the left there. You can see this coincides with a change from spin down behavior to kind of a plateau in the changes in the pulse frequency. We also, in our paper, we have something about another one. We have a possible system in it. I'm not sure if I have enough time to talk much about it today, but this is another Wind-Accretion system, 910-second pulse period. I'm not sure what the companion is. And previously, we saw a hint of a almost 15-day superorbital period. So we wanted to look with a longer-term light curve to see what's going on there. So we do similar things to what we did 1538. In the bottom is the entire light curve. And the peak you see there is actually the orbital modulation. In the middle one, we got rid of the eclipses, similar to 1538. You see a couple of blips there. But the candidate modulation is actually not very sinusoidal. If you look at the paper, you see it more clearly there. So what we do, we sum the harmonics. We sum the 3 harmonics in the top panel with the eclipses removed. And we see something which is looking like a hint of a real modulation now. The 2-dimensional power spectrum shows that the modulation of its real was stronger later on, but it's not been there for some time. Now we've put 1538 on the plot of superorbital period against orbital period. That's in the bottom panel. The top is the ratio of the superorbital period to the orbital period. 1538 agrees extremely nicely with a proposed correlation between the orbital period and superorbital period. Note that 1538 is the only one which has the exact ratio between the two periods. 16418 looks very close in the plot, but there is a significant difference, statistically significant difference between being an exact ratio. So we went back and revisited the models, and particularly we interpreted the data in using this model proposed by Botso et al. In 2017. This is based on the idea that there is a structure which we know exists in the wind of a supergiant system, and it's co-rotating with a primary star. But if the primary is not exactly co-rotating with the orbital period, then you'll see modulation at the beat period between the superorbital period and the rotation period. So you see a beat between the orbital period and the rotation periods, neutron star going through density. So the superorbital frequency is equal to the frequency difference of the rotation and the orbital period. So in this little cartoon here, we see the neutron star rotating more rapidly on the right than the system, and we get increase. Now the structure can also change with time, which can lead to changes in the profile. Although the period stays fixed, profile will change. So if you calculate what the implied CIR period is, and plot it against the orbital period, we get an incredibly high correlation. I mean, I was shocked by how strong this correlation is. It's a coefficient of 0.9997. Mathematically, it's actually not surprising, but physically, it implies that if this is the actual mechanism, there is an extremely strong correlation going on there, strong connection between the co-rotation period and the orbital period. Now, there is actually an ambiguity here because the neutron star could be rotating more slowly than the period. So we don't know which is the case, or is it going more or less quickly. So in the bottom panel here, we have, similar to the one I showed before, we have the two cases plotted separately. In either case, you get an extremely strong correlation with either the CIR is rotating more or less quickly than the orbital frequency. Now, in principle, you could have one in some cases, one or the other, but maybe by Occam's razor, you prefer that they are all going more or less slightly rotating. They're all going either faster or they're all going slower. It may not necessarily be the case, but the very strong correlation is suggested. You see the ratio of CIR to the orbital above. You see there's a modest difference. And for 1538, the CIR period is a nice fraction of that. So what could cause a modest deviation from orbital synchronization? If you have an eccentric orbit, then synchronization will be driven by the orbital velocity at periastron, which could cause the star, the CIR, to rotate faster than the orbital. Alternatively, if you have differential rotation in the primary, and the CIRs are not tied to spots in the equator, but spots higher up. So in one possible case, this O4 supergiant, these authors propose that the CIR was rotating faster than the equator. And in some late type stars, Kepler observation suggests that at higher latitudes, the rotation is slower than synchronous. Now we've been continuing to monitor 1538, and we see that it went from this kind of plateau to spinning up rather than spin down change, which we've seen before. And we're seeing perhaps a little hint that the superorbital modulation has come back again, although the statistics are not very strong. A lot of these periods are not that strong for the bat. If you accumulate enough data, they come out, but we have problems when the period is coming and going. So I actually got through that faster than I expected. I must be talking even more quickly than usual today, so sorry about that. So in conclusion, to kind of how we can follow this up a bit further, we notice that superorbital modulation can vary in strength and in profile. This possibly connected with changes in the spin period, and changes in the torque there. Maybe those changes are periodic, or maybe they're just stochastic. So what we really want to do is monitor spin periods in other systems to determine whether there's a connection with superorbital periods. Previously, it had been also suggested for 0114. So we're going to continue to monitor 1538 with the BAT and the GBM, these great all-sky monitors. We also have observations of 1538 minus 52, a maximum minimum to obtain with NICER. And my colleague Nazma Islam is preparing a paper on that. So can we show also that the CIRs actually exist and they're rotating that period? So possibly by doing high resolution spectroscopy in the optical and UV, we could see the changes in those periods. For 1538, we have photometry at the very end, which didn't show anything definite, but we're going to continue that more extensive, which in collaboration with Paul Roche. 1538, it would be great. So actually, one of my points is that more sensitive all-sky monitors would be wonderful. You have a constant period, you can just accumulate more and more data, but one thing that changes that, increased orbital and gray sensitivity is important. So the things in bold where I think EXTP may contribute. So in summary, superorbital modulation is likely telling us something important about the primary star, its wind and the accretion properties, but we just have to figure out exactly what's going on there. Thanks very much.
Thank you very much. It's very interesting. Any questions? Looks like a new Corbet diagram is showing up. Based on that model that you estimate, CRA, can you go and check whether there is any evidence of eclipse in the data? Since the strength varies quite a lot, as you said.
Oh, for the CIR, the CIR being eclipsed.
Right.
Yeah, I mean, it's sort of that fits into the general approach, which I mean we've mentioned it as a general thing we're interested in, and I think that's somewhere where it'd be good to collaborate with people who are kind of these experts in getting high resolution images to see what these components are in the wind. Hopefully, that is kind of one of the driving things is that the suggestion is that if we can see evidence of this structure, we would hope that it would be modulated on the period of which it is going around the primary star, and as you say, being occulted by the primary star, which will potentially give us a direct confirmation of the CIR and the rotation period, or we may find something else like star spots, which could be visible with enough precision. Perhaps from our continued photometry there.
Right. Sounds very interesting in either way.
Thank you.
Thank you so much.